Since 1903, man has had the ability to fly across considerable distances with the help of careful calculations, brilliant engineering, and human ingenuity. But as technology developed, so did our ideas and methods in achieving flight. However, the common denominator in all commercial and military aircraft is the presence of a wing that generates lift. From the shape to the length, materials used, and even the choice of paint, the wings of an aircraft hold up hundreds of metric tons of metal with the confusing sciences of aerodynamics and materials. This is the cross section of a wing, and it has a leading edge and a trailing edge. The chord is the line that connects the trailing edge and leading edge of the wing. The camber line is the line that connects the midpoints between the upper and lower surfaces of the wing. The angle of attack is the angle between the chord line and the direction of the relative wind. Now, let's take a look at the internal structure of a wing. The ribs are the structural member of the wing that determines the camber or shape of the wing. The spars are the structures that run through the length of the wing and bear most of the load. In the empty spaces between the ribs, there may be tanks that contain fuel in addition to the main tank. Finally, the outer layer of the wing is known as the skin, which provides an aerodynamic shape. Now that we know the internal parts of the wing and some of the terminology, it will be easier to understand exactly how lift is generated. However, the airfoil shape that I showed you earlier is not the only one that is in use. The one I showed you is the general airfoil shape that is used in older aircraft. But there are others too. The airfoil most common in modern aircraft that you would see flying around today is the supercritical airfoil. To understand what distinguishes these two airfoils, let's take the simpler one, which is the general airfoil, and understand how this one generates lift. First of all, you should understand exactly what the word lift means. Lift is a mechanical force that acts perpendicular to the direction of motion. Now, this direction of motion I'm talking about can also be called the relative wind direction, which I showed you earlier in the video. It is important to note that lift cannot occur if there is no airflow, and furthermore, lift cannot occur if the airfoil or wing is not in contact with the airflow. So, how is lift generated? Well, to put it simply, lift is generated by the turning of the airflow around a wing. There are many theories about how a wing does this, but most of them are incorrect. For example, the so called skipping stone theory, which suggests that air molecules strike the bottom of the wing, producing an upwards reaction force that is said to be lift. This theory only focuses on the bottom surface of a wing, though, and completely neglects the upper surface and its role in generating lift. However, if you look at a video of an airfoil in a wind tunnel, you will see that the upper surface also turns the airflow in a specific direction. In fact, it turns the airflow more than the bottom surface does. Another theory, which is widely used in textbooks and at the school level, is the theory of equal transit times. This theory establishes that air flowing on top of the wing and the air flowing below the wing must meet up at the same time at the trailing edge of the wing. This leads to the air above the wing accelerating as it has to cover a longer distance due to the curvature of the upper surface, and thus a pressure difference is created, causing the lift force to be produced. However, there is no physically correct explanation for why the airflow above and below the wing have to meet up at the same time. Therefore, it is incorrect. That being said, completely understanding lift is something that requires years of study and attention. The best the average person could do is grasp the basic concepts, which is what I'm going to focus on. Despite the last two theories being incorrect, they did have some correct ideas. For example, the skipping stone theory was correct about the involvement of Newton's laws and resultant forces, but got the surfaces wrong. The idea of pressure differences in the theory of equal transit time is correct, but the reason that the air accelerates is not. A simple, mostly complete theory of how lift is produced stems from combining the ideas of pressure differences or Bernoulli's principles as well as Newton's laws with a little bit of fluid dynamics. Alright, let's take our airfoil and place it in a wind tunnel where it is exposed to a flow of air. Here, we can see that the air flows around the airfoil and that is shown by these streamlines. Now here you will notice that there is something that I haven't included in any of the other diagrams, and that is this vortex here, which is called the starting vortex. The reason it's here is because of the air's inability to make sharp turns around the wing, and also due to viscosity. This vortex, if you look closely, is spinning in the anti-clockwise direction. Because of this, we can say that it has angular momentum. A well known rule in physics is that momentum, and thus angular momentum as well, should be conserved. If the angular momentum is conserved, then there must be a motion that acts in the clockwise direction opposite to that of the vortex. This takes the form of a circulation of air around the airfoil. Now, remember how the air was also flowing around the wing at the beginning? Well, now there is an additional flow of air around the wing, which contributes to the velocity of the flow. We know that velocity is a vector quantity, and so when we add together the two flows of air, we end up with air flowing faster on top of the wing and air flowing slower underneath the wing. Finally, according to Bernoulli's principle, air pressure is inversely proportional to the velocity, and as a result, a low pressure zone forms above the wing while a high pressure zone forms below the wing. This difference in pressure leads to the upwards force of lift. Well, after all of that, you may think everything is done and explained, but the problem is, it does not explain how airplanes are able to do this. Yeah, flying upside down is physically possible. It's not just a scene from a movie. The thing is, if we take our same airfoil here with the pressure differences and flip it, we will notice that the lift force is now acting downwards. That is not ideal at all. If we want to still generate lift while the plane is flying in whatever angle, we are going to have to bring in Isaac Newton. Using his laws, we get a much simpler but more general idea of how a wing can also generate lift. To start, the airflow around a wing will appear to take the shape of the airfoil. This is due to the viscosity or thickness of the air, which allows for the streamlines to be shaped in this way. The airflow around the wing is directed downwards to the shape of the airfoil, producing a downwash of air. According to Newton's third law, every action has an equal and opposite reaction, and therefore, due to there being a downwash, there must be an upwards force as well, which is essentially lift. Now, let's go back to our problem. We want this airfoil to work upside down too. So, we still need to somehow direct air downwards. The way this would work is, while the plane is flying upside down, the angle of attack could be increased, which leads to a stronger downwash, and thus a stronger lift force which keeps the airplane in the air, even whilst flying upside down. So, now that we know how exactly our airfoil produces lift, how exactly does the supercritical airfoil used in modern aircraft differ from this? Well, not much changes except for performance improvements. Our general airfoil is great and all, but only in aircraft flying below the speed of sound. The second our airfoil is going near the speed of sound, the airflow above the wing will be accelerated past the speed of sound, producing a shock wave on top of the wing which severely reduces lift. But the supercritical airfoil has a flatter upper surface, so air is accelerated less. Now, this does reduce the total lift produced by the wing, but that's why this small dent in the trailing edge is there. This area helps restore any lift that is lost by the lack of curvature in the upper surface of the airfoil. So, the main takeaway is the supercritical airfoil helps aircraft to fly at a faster speed without experiencing sudden losses in lift. Here we have a video of an Airbus A330 about to land. A special thanks goes out to Plane Spotting Berlin for allowing the use of this footage. You can find their channel in the description below. I will be using this video to explain the flight control surfaces on the wing. To start, let's go from the trailing edge to the leading edge of this wing. In this footage, at this moment you can see that a structure is being extended out of the trailing edge of the wing. These are the flaps. When an airplane is landing, it is often optimal to go as slow as possible to reduce the distance needed to bring the plane to a stop. But the issue is, the slower the plane goes, the less air that flows around the wing, leading to decreased lift. However, speed is not the only factor that determines how much lift is generated by a wing. If you think back to the last part of this video, one key factor that can also determine the lift generated is the area of the wing. If there is a larger area, then the volume of air that comes into contact with the wing will increase. Hence, the pressure difference above and below the wing will be increased. Therefore, in a situation such as a landing, where you need to fly as slow as possible but still maintain enough lift to make it to the airport, you can increase the area of the wing. But how does the wing do this mid flight? This is where the flaps come in. They extend outwards, like so, to increase the area of the wing. As a result, the pilot is able to fly the plane slower but not sacrifice its capability to generate lift to a concerning extent. Flaps are also used when the plane is taking off, which allow it to use less runway to lift itself into the air. It is important to note that the leading edge of the wing also has a similar structure known as the slats, which increase the area of the wing in the forward direction. Now let's move our focus to the far corner of this wing, where you can see this structure right at the edge. It looks a little bit like a flap, but it's not. These are called the ailerons, and they are what allow the plane to turn or control its roll. The way the ailerons do this is by the same principle that governs the overall shape of the wing and the lift it produces. When the ailerons are deflected downwards, the angle of attack in that area of the wing will increase, while the angle of attack in the other wing will decrease. Due to this motion, that area of the wing will generate more lift, causing that wing to tilt upwards. This leads to one wing tilting upwards while the other wing tilting in the opposite direction to counteract the movement. As a result, the plane is in a position where the pilots can pull back on the joystick to turn the plane. Finally, let's take a look at these structures near the middle of the wing. They are known as the spoilers or speed brakes, and by the second term, you can easily guess what they do. But how do they achieve this? Let's take an example from this footage. Once the plane has touched down on the runway, you can see that the spoilers will deflect upwards. This creates drag as it opposes the airflow around the wing, allowing the plane to slow down. Keep in mind though, the spoilers are also used in flight sometimes under specific conditions, such as during turns, in which they work together with the ailerons to reduce lift on one wing or to enhance the rolling effect.